Can you guys hear me? Okay. So yeah, I'm going to be talking about the Reproducible Build project, but I figure, like any good slideshow, there we go. We need to have a bit about me. It's not a real talk unless I talk about myself. More than anything, I'm just some guy. I use free and open source software in my spare time as a hobbyist, and I use it at work as a professional. And I'm sure that this probably relates to a good number of you guys in the audience. I am aware I have a funny accent. It's not Australian, it's British. So deal with it. If I say anything inappropriate or incorrect, sorry. Aside from that, and aside from using FOSS stuff for over a decade and a half, contributing patches and generally hacking and doing stuff, I seem to be collecting cats at an alarming rate. I've seemed to have acquired a single cat every year I've been in Canada. This is not a sustainable process. I'm not planning on getting another one next year, but that's me. So, spoiler alert. First of all, hooray for Debian. I'm going to be using a lot of examples from the Debian projects. That said, a lot of the principles and ideas, they do apply to other operating systems, other distros like Fedora and Arch, operating systems like FreeBSD. And there are also some software projects using these principles and ideas behind reproducible builds. So don't think this is a Debian talk or me pushing you guys into using Debian at all. It applies elsewhere. So let's set the scene. How do we make software? Where does software come from? So typically you have three main components. You have your developers, you have the internet, and you have your users. Your developers will normally author, compile, and package their code. So that will include going from the human-readable source code to producing a binary blob that the computer may execute, or that source code being packaged up as a zip, tar, RPM, deb, whatever. But they'll normally be responsible for these kind of activities. Once they've got their software built and they're fairly confident it works, it goes out on the internet, so it's accessible. So this binary file will be copied, be distributed to hosting sites, mirrors, replicated, and generally made accessible. And then subsequently, the user will come in and they'll be in a position of downloading that package or that binary blob, trusting it that it is what it claims to be or what they think it is, and using it. Sounds great, right? In an ideal world, this very high-level overview tends to be what happens, but it's not the case. As we're aware, at every single stage of the software development process, there is opportunity for problems because it's computers. Computers always go wrong, which is great. So this is by no means an exhaustive list of what does go wrong, but to give an example of things that we've identified as a community, as developers and as practitioners writing software and maintaining it, there's questions around, author identity. How do you know the person who wrote that software is who they claim to be, or is indeed, a credible person? The code being visible, how do we know what's even going into the code, the changes being proposed, the changes actually being accepted? Transmission errors can occur when downloading the content through just network failures. And we can also have intentional tampering of communications, man-in-the-middle attacks, DNS spoofing, and the ilk. There's also concerns around 0 days or disclosures of sensitive information and security bugs, and how we react to those. And of course, as users use software, we always find stuff's broken, perhaps unintentionally. But fortunately, as an industry, we also have acknowledged that some of these problems and come up with solutions as well. So ideas around GPG signing to give credibility of who made the commits and also who made this package. And I just realized my voice went there. We also have code PRs, peer reviews, pull requests. We can audit what are the changes being made. Is the backdoor being pushed into this package or not? Checksumming is available for once we've published a package and we download it, we can compare that our downloaded package is indeed what it should be and hasn't been corrupted. We can encrypt our communications as well. And then there are things around rapid release cycles and the community being engaged and being able to provide that feedback, being able to identify bugs, flaws, or call out unintentional and nasty things that may be brewing as a result of a code change or a feature change. And of course, if we're still not happy with any of these kind of solutions giving us enough trust behind what we're downloading is what we think it is, and it is indeed the right thing, just build it yourself from source, right? That's really durable. But who the hell actually bothers with that? Let's be realistic here. I'm sure there's probably some Gentoo users in here, so sorry. But the vast majority of us, we don't build software. We'll just take a pre-built binary and will accept it as it's ready and it's good to go. So it's worth identifying why don't people bother building stuff themselves. It turns into a huge yak-shaving exercise. Trying to create a build system or trying to create an environment that you can build the software, it isn't an easy task. It's much easier said than done. The first concern, time. It takes a lot of time to even get into the position of being able to build that software. And that's as a result of perhaps having to reverse engineer how the software was built elsewhere or was intended to be built. Some projects are better than others. Some will have nice descriptive make files and readmes and documentation. Others are just a huge nebulous black box of, oh God, what the hell is going on here? What were they thinking? How do I build this? And I'm sure we're all familiar with certain projects to which this applies. The hardware may need provisioning. For those of us in a corporate environment, this can be a real ball ache. Going to corporate IT, hey, we need another machine or a virtual machine that's running the right operating system or has enough capacity or whatever to build the software. It's time, it's effort. We can figure out the software needed, but then we need to actually get it. How do we make sure we've got the right version of the packages? How do we even make sure that we can access those packages in the first place? They may not necessarily be available to us as end users because they may be based upon internal build tools. And then subsequently, if they do manage to go through this major pain in the ass and actually build something, you're left with a binary blob, but is the build actually right? I mean, it built, but was it successful? So either way, either through downloading a binary that's provided to us by a third party and via the internet, or by building it ourselves, we're left with the question, how do we know that our binary, be it downloaded or built, is indeed what we think it is, and is indeed going to work? So this is where Reproducible Builds now steps in. So I've stolen this straight from the reproduciblebuilds.org website, but the long and short of it is, it's a set of software development practices that create an independently verifiable path from the source code that we first write that's human readable to the binary code being used by the computers, so the unreadable blob. I don't know how many of you can read binary, but I certainly can't. So it's also worth acknowledging as well that this is not a complete security solution in and of itself. It needs to complement other practices. And this is where things like GPG signing checksums, TLS, and all the rest of it, none of those are complete security solutions in and of themselves. They all just contribute towards this idea of building a collective model and idea of trust, that we trust what we're using, that we have confidence in what we're getting, and it is indeed what we think it is. So, the underlying principles from reproducible builds. The first one is a deterministic build system output. So by that, we need a build system whereby transforming a given source, every time we pass it through, it must always give the same results. It must always create the same binary compiled end item. Secondly, we need to define the build environment. So not only does the build environment need to be deterministic, it needs to be described and something we can communicate to other people. It's something that other people can look at and go, this is the software they're using. This is the version of the tools they're using. And thus, we remove that barrier of what the hell are they using to build this in the first place? What version of GCC was it? And then finally, we are left with allowing others to validate and compare their outputs. They've got a build system, they've got one which has been built to the spec of the build environment that's been defined, they've built a binary blob, and they now need the means in which they can take their binary blob and say, is it indeed comparable to one built elsewhere by someone else or by the official maintainers of the software? So there's a lot of focus here on the build system, and this is a bit of an aside from reproducible builds itself, and this branches into other good software development practices. But the emphasis on the build system here is something I feel is important, because how often have any of us been in, again, corporate or professional environments where there's a concept of the build system, and there's this big nebulous black box of obscurity that no one really knows about, but it's just there. We appreciate it's there, we just assume it's going to work, and people forget about it. It's just, the build system is great, it works. When it doesn't, you're blocked and you're stuck. So this is shifting the focus a bit more to treating the build system better. So one of the first things one of the first kind of principles that we're recurring with addressing the build system is automation. Automate as much as you can with your build system. You reduce the element or the possibility of human error when you make builds. And this can be silly things like someone forgetting to do some obscure step like write a certain file, move a certain file to a certain directory. automate it. Remove the risk of a human fucking up. It happens. Not too long ago, actually, at my workplace, we were trying to acquire a new version of a pip Python package, which allegedly had a fix for some bug we encountered. We downloaded the new version, still didn't work. Turned out the maintainer of the project had just rebuilt the old git tag and forgotten to bump something in the manual build process and acknowledged, crap, we should probably automate this. Secondly, make your build system open-ish. So by that, give transparency, define your build system more, be able to communicate what is your build system, what is going on in there. Far too often, build systems are just this obscure chain of code goes in, binary comes out. Right? Not quite. With regards to making it open-ish, there are certainly acknowledgements that need to be made as well towards sensitivity of certain bits of code or certain things going through that build system. So an example here was not too long ago, Canonical, who provide the cloud images for Ubuntu in AWS, Azure, and so forth. Their build system used to be fairly open. They've moved towards closing off certain parts of it and making it secret. The reason for this is it's partly political and it's partly due to legal reasons, but they may be including certain code changes in their build which refer to certain Intel microcode exploits, which I'm sure never happen. So certainly, you've got to make it as open as you can, but be aware of, what are the limitations of making it open. And then finally, acknowledge the value of your build system. It's a target. It's got a big, huge kick me sign on the back. Just think, if someone was trying to take malicious action towards you or your projects, rather than going after the user's machines, if they could go towards your build system, the ramifications and the influence that this have is massive. So really, treat your build system as a first-class citizen and give it as much scrutiny and as much auditing as perhaps people pay towards code with peer reviews and making sure 2 people sign off and there's approval. The same applies to your build system. And this ties into that horrible DevOps word, but platforms as code, defining your build system as code, and you can do this through automating it and so forth. But this is more of an aside about the build system and my complaint that build systems are generally a bit shit in the real world. So, coming back to reproducible builds, let's take a look at the history. It's not a new idea. This was a snippet taken from the Debian development mailing list back in 2007, where someone just posited the idea, hey, if we build the same package 3 times in a row, if we could diff it and check if there's any binary differences, we could then be able to infer if there's something being compromised in the build process or the build systems itself. Isn't this a great idea? I'm sure that the idea is even older than this instance here in 2007 and may have been mentioned elsewhere, but just in terms of Debian, here's a nice example where someone brought it up. It wasn't received well, though. One of the first major complaints was, it's pointless. What's the point? We've got new PG, we've got checksums, we've got MD5 sum. Why bother? What's the point of binary differing? Don't bother. The other criticism was, it's not feasible, or it's not technically feasible or worthwhile to do. So in this instance here, this person mentions, hey, he's happy to be proved wrong, so hopefully by the end of this talk, we'll have a happy individual. Nevertheless, a first try was attempted by a couple of folks in the Debian team. This was back in DebConf 13. They kicked off a small project with about 30 or so hackers who basically went, you know what, screw it. Let's try. Let's see what happens if we do try this bit differing of Debian packages. So their approach basically boiled down to, let's record the existing build environments and the existing Debian build system. Let's try to replicate it. And then if we start changing certain variables in that build system and in that build process, what breaks, what influence do these variables actually have in terms of producing different output of binaries? So from this very rudimentary attempt of replicating the build system, a number of variations or a number of sources of variation were identified. And some of these will perhaps be obvious, things like if you're not using the same software version of Make and GCC, it's going to give you a different output. The same goes for using a different operating system or a different version as well. Other obvious things, perhaps, the timestamps. Depending what time you build your binary, you might be injecting these into log files, and thus the binary will differ. Also the path as well, where on the disk were you building, or where were the files that were being built on the path, where were they stored? The list does go on though. File ordering, that's a bit obscure. Depending what order the operating system read the files off disk or the file system reported it, you could get differences in your built binary. We're getting a bit obscure now. And the list starts to go on. locales, network settings, the host name of the machine, the username making the build, even the output of uname as well. All of these things could create variance in your built binary. So yeah, you name it, it probably broke it. So in identifying all of these sources of variation, the next approach was, let's lock them down. Let's try to reduce this variation and then see if we get any closer to being able to do bit-differable binaries. So the approach taken here was start with the hardware and work your way down. Hardware first, let's stop using physical machines, virtual machines, and using disk snapshots. These are now the build environments that represent what things are being built under. And this ties into being able to have disposable build instances. I mean, again, how often have we heard about the build system at work, and when it breaks, everything grinds to a halt. Instead, by having virtual machines and snapshots, we're moving towards the idea of the build system may be precious, but we can replace it because we have the technology. The second step was then focusing on the environment or the software side of things. So using CH roots, fairly well adopted, well-known, old kind of Unix standard. Just use these to kind of lock down the file paths and then see how far this goes towards fixing these sorts of variation. On aspects of timestamps affecting things, there was a fantastic package out there called libfaketime, and you'll never guess what it does, but it allows you to fake the time as seen by an application or process. And it does this by intercepting system calls for requests for the time. So it's worth checking out in your spare time for shits and giggles. The third step was then, we've got the hardware set up, we've got the software controlled, what about the build scripts themselves and the way that they're working? Are they necessarily correct? Not always. In some cases, when they were building Java packages, there were timestamps being injected, and they weren't needed in the outputted build anyway. So just changing how certain dependencies were called by using the no timestamps flag, the same for tar, using -n and gzip, we can reduce these sources of variation, and we can also actually cut down the size of the binary we produce by cutting all the crap out. So, take two. We've tried to lock down things from our first rudimentary approach. We've tried locking things down a bit. Let's see what happens. So, taking a sample of 5,000 or so packages, this team then pumped it through this pipeline and, come on, almost 2/3 were reproducible. They could be built multiple times, and you could diff them, and bit for bit, these binaries were identical. And not just that, of those 3,000 or so packages, it includes some fairly big and commonly used things like wget and find utils. So it's not like this is just obscure small packages no one cares about. It includes really kind of far-reaching packages that a lot of people will be using. Of the almost 2,000 or so that weren't reproducible, identifying again what was the source of variation there, it was a long tail of variation. I mean, for the most part, it was things like the build ID being injected into the build. Again, it's needless, so if we correct that and remove that, we can have something closer towards being reproducible. I'm not going to go through all the list of all the different types of sources of variation, how they're fixed and addressed, because I'd be here forever. So let's step forward 4 years. Where are we now? So the Debian project's been adopting this process, and they're at the point where I believe over 90% of the packages offered in Stretch for AMD64, they're reproducible. They can build these packages multiple times on different machines even, at different points in time, and always produce the same outputted binary, which means they can now diff them, and if one build were to introduce a signature which wasn't the same, that raises concerns. Has that system been compromised? Has it got the right source code? Has it got what we think it's got in it? This 90% kind of mark, this wasn't easy work. Like I said, it was 4 years of fast forwarding through time, but it was achieved by basically influencing wide-reaching kind of concerns within Debian itself. So this went from things like the policy on how depackage is used, their packaging tools. This was addressed, and in terms of our everyday lives, this relates to, if we want to achieve something that's more reproducible in our own builds, updating and adjusting our build tools. Just because it builds something currently doesn't mean we're using those tools correctly. Think back to those Java doc calls and why we're including timestamps. We can cut down the crap, and we can use our build tools in a better fashion than they currently are. They changed a lot of the hardware they run things on. They moved from fixed hosts to running a lot of virtual machines, which was very graciously donated. But again, this ties into the concept. Don't treat your build system like this precious thing that has to stay up and has to be well maintained. It's disposable. Make it such that you can tear it down, spin a new one up. Not only will it give you better ease in responding to certain incidents, should they happen, but also in terms of just scaling up your workflow or kind of replacing stuff as hardware fails. It's nice to be able to be in a position to replace your build infrastructure quite quickly. Within the Debian kind of release policies and the pipelines, they updated these to actually say that conditions towards making the packages reproducible is now part of the standard and something that package maintainers will need to work towards. It was thus then enforced. So it wasn't just a side project. As it gained steam and popularity, it was actually tied into the official process, as it were, and made, this is how we're going to do stuff. And it made people subsequently have to make their packages conform. And aside from the packages within the Debian context itself, this also fed into relations with upstream code providers, submitting PRs to third-party projects to correct the tooling they're using, to make their builds more reproducible down the line. Now, there is a caveat to all of this. Just because we can make builds reproducible and we can start bit diffing them and we can compare the signatures, like I said, it's not a security solution by itself. It's part of a wider solution of being able to order what code we're running and building up trust. So used in conjunction, used in conjunction, it facilitates the ability to increase that trust. But by not having reproducible builds, this in itself is not representative of a vulnerability or a fault in the package. That said, more work is certainly needed on the project. It's gained a lot of steam. Some great progress has been made, but it's still got a ways to go yet. Things like having independently verifiable and submittable signatures of packages, such that we can check that even though they're saying the package produces this signature, we can check third parties who have independently built it as well and check that they are not provided loaded results or flawed results. There's also expanding the project into being able to build the kernel itself in a reproducible manner. So there is the same kernel project going on within Debian. It's not in the mainstream build line of Debian yet, but they are at the point where they can reproducibly build the Linux kernel. So, yeah, time's up, but I'd just like to thank the Debian Reproducible Builds contributors for their amazing progress and the Reproducible Builds project itself for maintaining this and pushing this kind of practice throughout the industry. And I'd like to thank you guys, and I don't think there's time for questions. Thank God for that. Thank you.